Welcome back to Integrated Science. I'm Miss Sparks. Today we're going to be talking about momentum, which is a collaboration or an extension of Newton's second law. So previously we've been talking about Newton's second law of motion, which you may remember is the idea that an object that has mass and an object that has a motion, an acceleration, is going to have a product of what kind of force is being acted upon it in order for it to kind of move, which is then in collaboration with Newton's first law with a balance or unbalance. And this is an unbalanced force that we're talking about as we move forward today. So we're going to incorporate what does this look like when objects are in motion. Momentum is actually a human-made scale of measurement, or I should say vector, because we're going to be using a direction with it too. So it goes back to our scale and vectors. So today we're going to kind of just talk about what this looks like, practice a couple of problems, and then we'll actually have an assignment where we'll be looking at how can we change the mass of an object and how does that look when it's free falling and an impact occurs when it collides with something else. So we have a couple simulations and activities that we'll be doing along with this. So make sure you get out your notes today. Please jot down everything that's underlined, just as always. And let me kind of pull this up for us here. So first off, just once again, momentum. This is a man-made measurement. So think about like if you've ever been in the car and you've been pulled over to get a speeding ticket. It's how fast you are actually moving at that point. Or baseball. It's baseball season right now at our household, and different pitches are thrown at different speeds depending on who is throwing, or maybe they're throwing a curveball versus a slider. Whatever it may be, is that the momentum can change, and sometimes even your momentum can change as well. So the definition, I do want you to get this down. Momentum is defined as the product of an object's mass and its velocity. And so I feel like we've used these terms quite a bit, and we're seeing them up again. Oops, sorry, didn't want that. I want my pen. There it is. Let me use this blue. So we have mass once again, and we have velocity. So remember, mass is how much a object is made up of, and weight is how much gravity is pulling on it. So we're going to be here on Earth, our mass and weight are very similar. So I might ask you to use your weight as the mass in some of the activities that we'll do. And then velocity is just what is the distance and time it takes for an object to travel. So it's our speed, but with a direction. So remember, it's our vector. Remember, we drew earlier, and I can pull this up here. We had this when we were talking about speed and velocity. Let me draw my 3 different types of vectors. You might remember our little arrows there. The dot represents just the object. If we draw a smaller arrow, that represents that it is a slower velocity. In this case, we're going to say momentum. And if we draw a longer arrow, it's going to be a faster velocity. So we're going to kind of go through and talk about what this looks like here. So our equation that we're going to use for momentum is very, very similar to a force. And I actually left them both on the whiteboard right here. Force, remember, is mass times acceleration, where momentum is mass times velocity. So once again, we're still looking at objects in motion. It's just that one is slightly different than the other. So we're going to use these 2 equations periodically. See if I can get them both on my screen there, to kind of help define different types of ways in which things move. The unit that we are going to use is kilograms times meters per second. So mass is measured in kilograms, and that's right there. I'm going to think about it that way. And then our velocity is meters per second with a direction. That's very important. That's what this is going to say down here. Velocity is a vector. And since a vector times scale is a vector, momentum is a vector as well. So meaning, once again, we're going to have our dot is our object, and then our arrow is going to represent which way it's going, which is, once again, a representative or a vector. How many arrows can I draw on one slide? That's what you're probably thinking. So once again, we have momentum, mass, times velocity. So let's just look at a real simple one here. This one says we have a 1,000-kilogram car. Very nice car. It looks like Bumblebee. Is moving due west at 17 meters per second. So 1,000 kilograms, and it's moving west at 17 meters per second. Find the momentum. So once again, we're just going to use our fun T-chart, which I'm sure you're just loving at this point, but hopefully you're getting the idea that why we use these is because we are starting to get lots of equations. So we don't know momentum, so we're going to leave that as our x value. Our mass is 1,000 kilograms. Always important to make sure we leave our values there. I always like to say no naked numbers. And then our velocity is 17 meters per second. And this one's not too bad. Once again, we're just multiplying them together. So remember, our equation is P stands for momentum equals the mass times the velocity. So we're just going to plug in now. So x is our variable, we don't know. And our mass is 1,000 kilograms. You would think I would get better at using this little pen with my finger, and I am not, unfortunately. So we have 1,000. And we're going to multiply that by 17 meters per second. And when we do that, you type it into your calculator and you should get 17,000. Just kind of think about this one's not too bad because we're just adding the zeros on there. So 17,000. And that is going to be measured again, once again, in our kilograms times our meters per second. So that seems like a lot of information there, but that is how momentum is measured. So 17,000 meters per second. Once again, same as force almost. We're just multiplying that mass, and instead of acceleration, this time we're just looking at the velocity because we're looking at that vector. So remember, this said west, so you can write west here if you want. Or if you want to think about north, south, east, west, you could also draw your arrow that way. And even if you wanted, you could put a W there. As long as you somehow represent the direction that it's moving. So sometimes we can also find the change in momentum, meaning that what it was starting at could have changed. Maybe it had a positive momentum or a negative momentum, meaning maybe it's sped up or it's slowed down. So using that same example from before, they're saying now the car is moving due west at 23 meters per second. Oops, I meant to take that out. Just don't even worry about that there. So if you want to write this down as an example. So once again, think about our T-chart here so we can kind of sift through this information. Except this time we're going to be looking at it kind of like our acceleration, where we have our final and our initial. So final and initial. Oops, I should have put, yeah, we're good. BI. And then let's fill in what we know here. So once again, they're asking for the momentum. So that's our variable. The car's weight hasn't changed from previously, so that's still 1,000 kilograms. And now we're saying the car is moving due west at 23, so it's sped up. Because you might remember from previously, it was only 17. Oops, let me put my meters per second there. So just a little extra step in this one, not too much. So all we're going to do is, once again, we're going to take our 1,000 and we're just going to find the difference between our velocities, which is 23, our final, minus 17, our initial. And so when we do that, that gives us 15 here. 23 minus 17 is 15. And we're still going to multiply this by 1,000. And when we do that, we get, we're now room there, 15,000. So that's our change. So these are examples that we've kind of already used before. And remember, that's kilograms per meter per second. I shouldn't have written it that way. It should be this way because we're not dividing it, we're multiplying them. And that is bad. Hopefully you get the idea. So same idea as acceleration. We're just kind of, once again, multi-stepping. So we're taking our ideas of acceleration and kind of applying it algebraically. Where this is going to come in handy is that we're going to be looking at a couple of different simulations where you're going to be colliding things. So it's going to start at one velocity and then end at another. And that's when we're going to have to plug in this information here. Here's another one. I'm going to let you try it out on your own. I'm just going to read it to you. A rubber ball has a mass of 70, that should be 0.75, depending on my typos here. 0.75 kilograms is dropped and strikes the floor with the initial velocity of 3.75 meters per second. It bounces back with a final velocity of 2.65 meters per second. Calculate the change in momentum of the rubber balls. And once again, let's set up our T-chart. I'm going to let you do this one. Mass, final velocity, minus initial velocity. I want you to try to go ahead, pause the video, and fill in your T-chart. And let's find the change in momentum. That's what they want us to find. So I'm even going to put, here's our variable. So plug in the mass, the final, and the initial, and see what you come up with. And then we're going to check that. Sorry about my typos up here. Hopefully that's not too confusing. Those are points. So one of the last things I want to talk about, though, with momentum is impulse, meaning that sometimes things collide, and with that there is a change in energy, and that's what this equation is talking about. And we're just going to use the ideas behind it. So impulse equals the average force. So now we're going back to that beginning part of what we talked about with Newton's second law. So our average force, F equals ma times times time. So that's where that first part of what we talked about, Newton's first law, kind of comes into play with our impulse. So where F is the average force and T is the time. Impulse also includes the direction that an object is pushed by the average force. And that's really important, that direction, meaning that there could be two objects coming at each other and they're going to collide at some point, and they don't just stop. Normally there's energy that's pushed one way or next. So think football. Football is a great example of this. So you have two players that are at the line, and I should not use football as an example because I'm not the best person understanding all football terms and everything. But when they collide, maybe one is stronger, has more mass, has more weight than the other, and they're gonna like plow over top of them. Or they could just collide and maybe they're almost equal and they just kind of sit there and gridlock. Another example, unfortunately, is like, think about car crashes. So sometimes when they come into collision together, how they hit is going to depend on how they spin back out, or they just don't just clunk and stop. There's normally like they clink and then move backwards. You maybe seen those crash test dummies or the video of them, and they always kind of like hit and then fall back. So that's what this impulse is saying. So impulse momentum, the theorem that tells us that impulse action of an object is equals to the change in momentum, and that change is what we're going to be focusing on. How does that change? How does that look like? So we're going to look at a couple simulations to kind of help develop our ideas behind this. So hopefully that was helpful, and go to our next portion where we're going to look at the simulations.